This is part 1 of the tutorial for lesson 9.1, Solving Systems of Linear Equations by Substitution. At the end of this lesson, you will be able to solve systems of linear equations algebraically using the substitution method. And there will be 2 parts to this video. Recall that in topic 8, we found the solutions to systems of linear equations by graphing the equations and finding the point of intersection. This might look like this. So if you had 2 lines on a graph, so the red line can be one line and the blue line can be another line of the system of linear equations, wherever they meet that point of intersection, x comma y, whatever those values were, was the solution to that system of linear equations. The values of the point of intersection were the 2 values that made both equations true. In topic 9, we find the same values, we find the same coordinate that would be the point of intersection, but we're going to do it algebraically instead of by graphing. What's nice about this is you can always take the 2 equations from the linear system and graph them to check your answer, to see if your answer is the same as the point of intersection. Alright, so here is a quick overview of the steps that need to be taken to solve a system of linear equations using the substitution method. I'm not going to go over them in any great detail right now because we will be using them as we solve the examples. Step 1 is to first isolate or solve for one of the variables in one of the equations. So you just pick one, and if you pick one that has a coefficient of 1, to isolate, it will be easier to isolate. Step 2 is to substitute the expression for the variable you just isolated into the other equation, and it's important that you use the other one. And then you'll notice that you only have one variable left, so you're going to solve for that remaining variable. Once you have the answer, or the number that that variable is equal to, you're going to use it to substitute into one of the original equations and solve for the other variable. Lastly, you can check your solution by substituting each value from your solution into the original equations and checking that the left side equals the right side, or by graphing the system and making sure that the intercept is your solution, just like we would have checked our answers in topic 8. Okay, so let's look at our first example. Here we have 2 equations. Equation 1 is 4x plus 5y equals 26, and equation 2 is 3x equals y minus 9. These are both linear equations, so let's solve for them algebraically using the substitution method. The first thing we need to do is pick one of the variables to isolate. If we look at all of the variables, we have 4x, 5y, 3x, and just y. We can choose any one of those 4 to isolate, but we want to try to pick the variable that has a coefficient of 1 because it will be the easiest to isolate. So if we pick this y value that's by it just has one y, we will isolate that. So step 1, we'll start off by rewriting the equation over here, and we got to get the y by itself. So we are going to move the negative 9 to the other side of the equation by adding it to both sides. And then we'll have just y equals from the right side of the equation above. And on the left side from above, we had 3x plus 9. So now we have an expression for y. We have that y is equal to 3x plus 9. So this takes us to step 2. We're going to substitute this expression for y into the first equation, the one that we didn't use to isolate y to begin with. So this was step 1 was from equation number 2. So now when we sub it in, we got to sub into equation 1. Alright, so let's write down our equation. 4x plus 5y equals 26. We know that y was equal to 3x plus 9, so we're going to replace it with that value. So we'll have 4x plus, and then 5, let's fix that here, 5 times whatever the y was equal to. which from above, y was equal to 3x plus 9. And then that equation was still equal to 26. So it's the same equation as the first equation, but we've replaced y with what it's equal to, the expression that it's equal to. So that is step 2, subbing in for your variable. For step 3, we're going to go ahead and solve for the remaining variable. Well, the remaining variable is just x because that's the only variable we have in all of this equation. So the first thing you're going to do to solve for x is to use the distributive property to expand the brackets or multiply out the brackets. So the 4x on the front will stay the same, and now 5 times 3x is 15x, and 5 times 9 is positive 45, and that's equal to 26. So there we've expanded our brackets. The next thing we can do is gather like terms. So our x terms are like terms. We're going to have 4x plus 15x is 19x plus 45 equals 26. Now we have just one x term, so we need to keep solving for x by isolating it. First thing we need to do is get rid of any addition or subtraction. So we'll get rid of the plus 45 by minusing 45 from both sides. And we're left with 19x on the left side and equals negative 19 on the right side, because 26 minus 45 is equal to negative 19. One more step now. To get x by itself, now we can divide by 19 on both sides, and x is left over on the left side, and negative 19 divided by positive 19 is negative 1. And that is our x value in our solution. But that's not our only answer for our solution. We're not done yet. We still have to find y. In order to find y, we go back to one of our original equations, and we're going to use this one where we isolated y from the second equation, and we're going to use it to solve for y. If y is equal to 3x plus 9, and we know that x is equal to negative 1, then y is equal to 3 times negative 1 plus 9, which is negative 3 plus 9, and that is equal to negative 6. So our solution then is the point negative 1 comma positive 6. Now you can always check your answer by either graphing the two equations when they're in y equals mx plus b form, or you can sub the answer, negative 1 comma 6, into each equation and make sure left side equals the right side. So 4 times negative 1, because that's what x was equal to, plus 5 times 6, because that's what y was equal to, should equal 26. So let's go ahead and solve the left side of this equation. 4 times negative 1 is negative 4, plus 5 times 6 is 30, equals 26. And negative 4 plus 30 is, in fact, equal to positive 26. So therefore, the left side equals the right side. So it worked for the first equation. But remember, it also has to work for the second equation. So we'll have 3 times negative 1 equals 6 minus 9. Well, 3 times negative 1 is negative 3, so that's the left side of the equation. And the right side of the equation, 6 minus 9, is also equal to negative 3. So it also works for the second equation. Therefore, because our solution, negative 1 comma 6, worked and for both equations, it satisfied both equations, it is the correct solution to the system of equations. In example 2, we have a system of linear equations where none of the coefficients are 1. We have 2x, 6y, 5x, and negative 3y. And we need to isolate one of those letters. So thinking ahead a little bit, I'm going to choose the 2x to isolate the x for. And the reason I chose that is because I'm going to think ahead a little bit And I know I'm going to have to divide by 2 to get x by itself, and the 6 and the 8 are both divisible by 2. So if I have 2x plus 6y equals 8, to get the x term by itself, we are going to subtract 6y from both sides. That leaves us with 2x equals negative 6y plus 8. Now we can go ahead and divide by 2, and we have to divide every term by 2. That leaves us with x equals negative 6y divided by 2 is negative 3y, and 8 divided by 2 is positive 4. So now we have an expression for x. X is equal to negative 3y plus 4. So I'm going to go and I'm going to sub that expression in for x in the other equation. So I have 5x minus 3y equals 20, and when x is equal to negative 3y, we can write negative 3y plus 4 in for x. And then minus 3y equals 20 will stay the same. Now we're going to use that distributive property here where we multiply the 5 into the brackets. So we're going to get 5 times negative 3, which is negative 15y, and 5 times 4 is plus 20. And then we have minus 3y equals 20, that stays the same. Now we can gather like terms, so we have negative 15y and negative 3y as like terms. Negative 15y minus 3y is negative 18y plus 20 equals 20. The rest of those terms stays the same. So let's subtract 20 from both sides to get the y term by itself. So we're left with negative 18y is equal to 0, because 20 minus 20 is 0. Last step is to divide both sides by negative 18, and y is equal to 0 still, because 0 divided by negative 18 is still 0. Alright, so now we have to take our expression for x that we had from above, so x was equal to negative 3y plus 4, and we're going to sub in the value of y, which was 0, that we just solved for. So x equals negative 3 times 0 plus 4. Solving for x, negative 3 times 0 is just 0, and so we have 0 plus 4, and 0 plus 4 is equal to just positive 4. So I can say that my solution is at 4, 0. That's when x equals 4 and y equals 0, it would be the point of intersection on the graph of these two lines. I can verify my answer by subbing x equals 4 and y equals 0 back into the x and y for the original two equations, and solving to make sure the left side equals the right side.